Salt is the most common groundwater contaminant. This map shows the depth of salt water across the U.S. The light pink color is an area where the groundwater or the salt water is less than 500 feet. So the fresh groundwater is really relatively shallow. Now, if we want to evaluate the freshwater aquifer and how it interacts with the underlying salt water, then we have to account for the density of the salt water. Adding salt to water increases its density, and if you add enough salt to, say, equal the salinity of seawater, then you have an increase in density of about 2.5%, and that's enough to affect how the groundwater flows. So to show you how to include density effects in groundwater models, we're going to turn to barrier islands. This is a barrier island. It's a long skinny island along the coast. Here are some other barrier islands along the coast of North Carolina. And these are underlain by sand and clay, and they often have freshwater aquifers developed within them. These freshwater aquifers are strongly interacting with salt water from the ocean, and the development of these freshwater aquifers will be what we're interested in simulating. So here's how we'll set up our model. This is a blow up of the picture we saw on the previous slide. There's 1 kilometer, and these islands are very long in this dimension, so we can make a cross section along this line, and we'll just simulate the 2D model that is a slice through this island. We'll assume that we have constant head on this side, the ocean, and then also constant head over here in the bay behind it. And we'll, at least at first, assume that the properties are uniform, and as a result of that, we have some recharge here, and that would cause a divide to form right here in the center. So our model will only consider 1/2 of the island, from the divide over here to the ocean. And so we take that slice, and here it is represented in a very idealized way. This will be the aquifer. We'll have a constant head boundary up here that will be the ocean. We'll have some recharge coming in along the top. That'll set up a flow system like so. And we'll assume that this region is initially completely filled with salt water. Say the ocean rises and submerges the island and then drops again. And the freshwater aquifer then will develop by flushing the salt water out with fresh recharge. Okay, so we'll set up a model of that. Here are the properties that we'll assume. The width is 500 meters, and we'll assume that it's 200 meters deep. That's actually pretty thick. But it'll serve our purposes to show how this system is set up. Now, when we do this simulation and include the effect of the density being affected by the concentration of salt in the water, then we really need to do 2 things. We have to have a simulation of the flow of the water and a simulation of the transport of the salt. And those 2 will be coupled together because as the concentration varies, the density of the water will vary, and that will affect the flow. So we'll assume that the saltwater concentration is 35 grams of salt or kilograms of salt per cubic meter, and the density of water is going to be a function of the concentration. So it'll be expressed with this linear function. The concentration is C, and that term is given down here. This causes the density to increase with concentration, and if C is equal to 0, then the density is 1,000 kilograms per cubic meter. Now, the function that's going to cause the density to increase is the concentration times this term here. We're assuming this is a constant, and it's given here, roughly 0.7. And this is dimensionless because it's kilograms per cubic meter per kilograms per cubic meter. But so those cancel out, but they're not really exactly the same dimension, because this is kilograms of water per cubic meter of water to give us a density of water, and this is concentration, kilograms of salt per cubic meter of water. So you can verify that these units will give you the correct units of density if we substitute in there. So in order to do this, we'll use JMS, and we'll set up a Modflow model to simulate the flow, an MT3D to do the transport, and we'll use seawat to do the, actually seawat will be used to do the transport, and it is similar to MT3D, and we'll use it along with MT3D, but seawat has the capability to have this density function in here. Okay, I'm going to set up a GMS model to simulate the conceptual model that we saw previously, and we'll make a grid that is 50 cells in X, 1 cell in Y, and 20 cells representing 200 units in the Z direction. So when we do that, we get a grid that looks like this, and we're looking down on this grid. If we look at it sideways, this is what we've got. So this is essentially, it's just a 2D grid, but we're doing it in 3D because we want to make it vertical. Okay, when I add the conceptual model, I want to make sure that I check transport, and I'll define the species as salt. And then I'll put in 2 coverages. This one I'll call properties, and we'll have that include the recharge rate, recharge concentration, the vertical and horizontal conductivity, the specific storage and specific yield, porosity, longitudinal dispersivity, and starting concentration, and we'll have it go from 1 to 200 layer or 20 layers. And we'll put in another coverage that will be, I'll just call it BC for boundary conditions, and it's a specified head boundary. Now before we put the attributes in, we need to go and make sure that we have the units set up properly. So let's change this to meters and seconds and kilograms. Force doesn't matter, but concentration, we're going to go and use mass per length. So the concentration will be done using the this mass, or well, actually, this mass, and then cubic meters. Okay, so now we can set up the attributes, and I put in a polygon, and here are the attributes from our setup problem. Let's see, I think all of these are straightforward. The salt recharge concentration is going to be 0, because we'll assume that the recharge is fresh, and that will flush out the salt water. And we'll also assume that initially the starting concentration of the salt is 35 kilograms per cubic meter. Everything else, I think, is as we specified on the slide. And let's see, for the boundary condition, we're going to put in well, actually, let's first put in put it in as an arc. So we'll draw a line here, and we'll say that that is a constant head arc, and the nodes are at 195. The top of the model is at 200, so it's an unconfined aquifer, so we'll have the head be just slightly below the top of the upper row, but it'll be, or the upper layer, but it'll be above the bottom of the upper layer. Okay, so now we got to put in Modflow, and we'll use a starting head of 200. And we should be able to map it and then run it. Look at it in cross section. So that looks about right. I think it'll look a little bit better if we change the way the contours are set up and use the color fill linear. So that's the pattern of the heads. We can see the difference between the head at the ocean and the head back here is only 1.2 meters, so a very low gradient. But this is a very flat area. That could be, it's a pretty high permeability, very thick aquifer. So there are the heads, and this will serve now as the starting heads for the next analysis that will have be a transient analysis. So we'll duplicate this. And switch under global options from steady state to transient. And now we'll add MT3D. We'll set up a stress period using this initialize button. And we're going to run a model for 10 to the 10th seconds. That's about 300 years. And we'll use 1,000 time steps, and everything else we'll have as the defaults. The output control, we've used this in the past, but it seems like with seawat that you cannot use this. So we're going to generate a lot of time steps, but when I experimented with using this as something other than one, basically it suppressed the output. So we'll keep that at 1. And the packages will be advection, dispersion, source, and sink. We need to define the species here, and this needs to be the same as what we used earlier for the conceptual model. The units should be okay, and the porosity we set up with the conceptual model. So we should be good here. Okay, so now we need to add, well actually, I forgot, we set up this initial head, so we need to go back here to our initial head in the Modflow model and select it. Okay, so we're set up to run MT3D, but we're going to put in a seawat model instead of running the MT3D. And to do that, we're going to right click on project and go to, you've been going here to new to add stuff, but we're going to go here to model interfaces and check off seawat. Then we see it appear up here, and we'll select a new simulation. Okay, so here's what you need to do. Check off include transport in the simulation and include variable density flow. seawat also allows us to have the viscosity vary with the salt content, but we're not going to use that now. Then we go back here. That was the global options, and we're going to also take a look at the VDF package. Okay, so what you need to do here is use a reference fluid density of 1000. That is the concentration of the water when the concentration of salt is 0. And the density factor term F on the slide is this term here. And there's the value. So that's the default value. We'll go with that. So that's what we need to do for this slide. And let's go and see how we're doing. So we'll map MT3D. Let's also map Modflow because we changed from steady to transient. And then let's go do a check simulation for MT3D. So that looks good. Well, okay, so we have this guy here. Let's check seawat, but we'll come back to that. So let's do a seawat check. Okay, so that looks good. Okay, so there was this this warning: concentration values or 0. Actually, that's fine. That's fine. But let me just give you a heads up about a problem that comes up in kind of a mysterious way. So if you go to Modflow optional packages RCH, this is the recharge package. We click that, and this checkbox, use previous. We don't want to use previous. This is the default, and this default can get reset by something that the software does. And so if you have troubles, particularly if you get some results that look peculiar, I would go back and see if this has been checked. That happened to me several times while I developed this example. Okay, so we should be good. We've mapped the Modflow, we've mapped the MT3D. There's no seawat to map. It works as if it's part of MT3D. And we've made the Modflow transient. And the reason we do that is because as the fresh water sweeps out the salt water, the density will change, and that will cause there to be some flow. Okay, so we'll go ahead and run the seawat model. This will be a transient model, and it takes longer to run than MT3D because it has to do the density calculation. And we're running it for a fairly long time, 1,000 time steps. So it'll take a little bit of time to simulate. Hopefully not too long. Okay, just about exactly a minute on my computer. If you get something much different than that, then perhaps there's something that's not set up correctly. Okay, so before we end, let's take a look at this. These are the results from the solver, and you can see we're at the 1,000 time step, and the total elapsed time is right there, 1E10. So it looks good. One thing you should also check is this box. Make sure that that is checked. If it's not checked and you hit close, then you won't be able to see any of the results. Okay, so here's the salt concentrations, and let's open this up a little bit. So here's the salt. The red is roughly 0, and so you can see that after that many seconds, about maybe 10-20% through our run, we're starting to develop a thin freshwater aquifer here. We go further down and it develops further, and so let's see, it's about halfway through, and you can see here this is the freshwater lens with salt water underneath it. So this is about halfway through, and we've got a layer that's let's see, that's cell 8 of 20, so we're not quite halfway. And then let's take it down here to 7.5. So you can see at 7.5 this is cell 9, so we go another quarter of the simulation and we really don't change it much. So this this is starting to reach kind of a stable point, and you can see now we go another quarter and it advances down. It's not really going to reach a steady state, but the rate of change is really slowing down. And well, actually, I guess this could go to a steady state. It won't do that in this time frame, but you can see that we got a lot of change at first, and then the rate at which it's changing drops off, and we've got this lens. This is all fresh water here, and then this is a transition zone where we've got some mixing, and this is all salt water. We have some kind of strange contours here. It's really just probably just some kind of a numerical artifact. But I think this looks pretty good for a freshwater lens that has been swept out by recharge of freshwater onto a barrier island. We can see the effect of the density on the simulation if we go back to the VDF package, and this parameter here, that's the F factor, if we set it to 0, then as the concentration changes, there will be no change in density. And this is essentially what is done by MT3D. We'll continue to use seawat rather than going back to MT3D because, well, the way the software is set up, what I found is that it's just best to stay and use seawat. If you go back to MT3D, or if you go back to Modflow, there are problems. So we'll set that to 0, and we'll map it again. Let's map both. Probably don't need Modflow, but we'll do it just to make sure. Update the files and then run them. Okay, so this will be just a repeat of the analysis, except we'll just assume the density stays constant. Okay, so simulation finished, and we'll take a look at the data set here, and we'll just go all the way to the end. So there's the result, and you can see that the freshwater is much thicker here, and essentially if we wouldn't have included density, we would have overestimated the thickness of the freshwater zone. And essentially what happens is the density of the water, the seawater, makes it more difficult to circulate that water out. So it's an important consideration. It really gives you a much different result. Um, One thing too that is a pretty interesting problem. This is really a stable problem where the light water, the light fluid, is overlying the denser fluid. But in some cases, for example, if you had a tsunami and inundated this area, then you would have a dense fluid over a light fluid, and you would have the salt water flowing downward as a result of density. That was indeed observed. So another effect that I wanted to show you is if we go and add in a low permeability layer. So the model that we've set up is very idealized, and that's fine. It gives us an idealized look at how this works. But we might want to consider the effect of a lens. Back here, well, this is symmetric, but this depositional environment has this back bay where there are a lot of fine-grained sediments deposited, and so it would be fairly common to have some clay lenses in this kind of a setting. So I went in and put in a low K layer. I added another coverage, and let's take a look at it in plan view. So here's the coverage over this part of the area, and this is gonna look like, well, the coverage is just the horizontal and vertical K, and I set it up to be 10 to the minus 9 meters per second. So that's the permeability of, or hydraulic conductivity of clay. And let's see, the coverage is from layer 4 to layer 5. So it includes 2 layers. So other than that, the model is the same. Now, ideally what we would do is rerun the hydraulic heads and have a different starting heads, because right now we have the starting heads that we got from the homogeneous case. So ideally we would go back and rerun that. However, what I've found is that if you go back and modify the Modflow simulation, particularly if you switch from transient back to steady state, then it will crash immediately, virtually every time. So we're not going to go back and mess around with the mod, avoid that. Okay, we can just go ahead and map this. We need to map it to the Modflow and MT3D, and then run seawat. Okay, so let's take a look at the results. We'll just go right directly to the end, and we'll look at it in cross-section. So we can see the effect of this lens. Here's the lens, and we can see that it's higher concentration than the freshwater. Remember, 100 or 1,000 parts per million, which would be 10 kilograms per cubic meter, right in here. Well, right about in there, the green. That is the freshwater, brackish water boundary. So this is brackish water here in this lens. See, we've got a little bit of fresh water that's managed to get underneath it, but the previous simulation had the freshwater lens go all the way to all the way like this, and so clearly this lens here would have dramatically affected the location and thickness of the freshwater lens.